All right, how's it going? Welcome back to another video here in the series on vector calculus. The last video was spent looking at examples for calculating line integrals. And one of the big concepts that we learned in the last video is that the value of the line integral actually changes depending on the path that you integrate along. And that's kind of this interesting idea that we don't necessarily see in single variable calculus, right? Because if you're just integrating a function f of x from a to b, then there's really only one direction which you could integrate along. I guess two. You could go in the positive x or negative x direction. But as you begin to work in an increasing number of dimensions, all of a sudden now there are many different paths you can take, and now all of a sudden specifying the path becomes important, right? So that was this idea that we looked at in the last video. But one thing that people might be wondering, and it would be very valid to wonder about this, is to say, well, when are the cases where the path doesn't matter? First, I guess maybe even asking the question, are there any cases, are there any line integrals that you could perform where it doesn't matter on the path that you take? And if there are, what are the circumstances where that is a valid assumption to make, right? And I'm just gonna answer the first question right away. First, the answer to the first question, are there integrals, line integrals where the path does not matter? And the answer is yes. It only applies though to certain types of vector fields. And you might be able to tell where I'm going with this by the title of the video, because the title of the video is conservative vector fields. There might be some correlation between the two. Okay. So we're going to talk all about vector field or conservative vector fields in this video and some of the nice convenient properties that they have. And we're going to go into a bunch of different things. So to start out the video, I want to just write out the definition for what a conservative vector field is. Then we're going to go through that together. All right, so we have the definition here for a conservative vector field. So let's go through that together. It says here that if uppercase f is the gradient of lowercase f for some scalar function lowercase f, then uppercase f is called a conservative vector field. Okay. So let's make sure that we just understand what this is saying. So a conservative vector field is simply defined as the gradient of a scalar function. So if you have a vector quantity and you're able to express it, or the quantity itself is able to be expressed in terms of the gradient of some scalar function, then that's when that vector field is conservative. Okay. Now, just to make sure that we're on the same page as to what's going on, and hopefully this will make sense, that f by its, or lowercase f by itself, it's a scalar function, meaning it does not have any, it's just a single component quantity. And then when we apply the gradient to it, then what we're inherently doing is we're operating on the scalar function and we're turning it into a vector function. And specifically, the vector function that we output is all of the partial derivatives of our scalar function. So in Cartesian coordinates, at least, as partial f, partial x, I hat plus partial f, partial y, j hat plus partial f, partial z, k hat. And this resulting vector right here, that is what uppercase f is going to be. Now, just another thing too, just so we're aware, the reason why it's called a conservative vector field, the naming is inspired by physics, actually. And the reason for it is because these types of vector fields, ones which can be expressed as gradients of scalar fields, those get used in physics to model certain types of forces. And they get used to model specific types of forces, specifically forces which conserve energy. So if you have a force and energy is conserved when applying that force, then that would be considered a conservative force modeled by a conservative vector field. All right. So it comes from physics. That's where the name comes from. All right. Now, just so we're familiar with this too, we might be saying, okay, sure, if we can express a vector field in terms of the gradient of a scalar field, then sure, we call it conservative. But we might ask, what's kind of the process for doing this? And we're going to get into that process, of course. But let's just ask ourselves, like, if we have a vector field and we say that vector field is conservative, we might be wondering, well, how do we know what this lowercase f is? How do we construct the lowercase f if we're provided this uppercase f quantity? Okay, and the basic idea is that you can more or less just match up vector components. So rather than writing just the vector uppercase f like this, I'm just going to rewrite it. So maybe it has, I'll write the uppercase vector f over here, and we can say that it has an x component along the I hat plus a y component along the j hat and a z component along the k hat direction. And again, the overall quantity is a vector, but each of the components, f of x, f of y, and f of z, of this vector are themselves scalar quantities. So what you can do is you can just match up the I hat with the I hat, j hat with the j hat, and k hat with the k hat. And I'll just work through the f or the I hat example, and then you could generalize to the other, the j hat and k hat basis vectors. So you would say that f of x equals partial f partial x, like this. And then what you could do is you could just integrate both sides with respect to x, right? And if you integrate both sides with respect to x, let me actually do this. Let me say, just put this on the other side. So if we were to then integrate, let's do this. If we were to integrate both sides with respect to x, from fundamental theorem of calculus, if you're differentiating something with respect to x and then integrating it with respect to x, right, those more or less cancel each other out, and you get your function, f of x comma y comma z. And then here, you're going to have some indefinite integral, and you're integrating over f of x, right? Now, let's say that you end up finding whatever the value of this integral is, right? And I don't know what to call it. What I'll just do is I'll just say that, I don't know, let's say that, I'm just going to do this. I'm going to say this a little squiggly. Let's say you integrate it, and whatever the value of that integral is, you get this, okay? Now, because it's an indefinite integral, you're going to have that integration constant that comes out front. So you're going to have that plus c at the end of whatever this thing is right here, right? Now, one thing that you're just going to want to be aware of is that now that if f is a scalar function, it's going to have inputs x, y, and z, right? And all we've done is we've integrated over x. So this term being a constant doesn't just mean that it is purely a constant itself, but in the most general case, c could be just a function of whatever two variables you didn't integrate over. Specifically, c in this case could be a function of y and z. And hopefully this makes sense, right? Because if c is in general a function of y and z, if we were to then differentiate both sides with respect to x, on the left-hand side we get partial f partial x, which is what we have right here. And on the right-hand side, we would end up, if we differentiated this, we would end up getting f of x right here, and then differentiating this with respect to x would give us 0. So this is a constant in the sense that it doesn't depend on x. So you could go through this process, and then what you would end up getting if you matched up each of these components is you would get an expression for f this way, and also for the y component and the z component, and you would have three different constants of integration. This would be a function of y and z. Integrating this, the j hat component would give you a constant of x and z, and the same thing for the k hat component. The integration constant would be a function of x and y. And then using those, you can kind of piece together what the overall scalar function lowercase f would need to be. Okay. So that is more or less the process in which you go about finding the lowercase scalar function f if you're given an uppercase vector field f, which is conservative. Okay. So hopefully that makes sense. Now, next thing that we want to do is to kind of just mention why do we care about these things. And we kind of mentioned it in the previous whiteboard when we started recording, but these types of vector fields have very convenient properties. So we're going to list out the main property that gets used for why people care about these things, and then we'll unpack that. All right. Now, one of the big kind of selling points for why we care about conservative vector fields is right here in this theorem. So let's go through it together. It says here that a vector field, or I should say, if we have a vector field that is the gradient of a scalar field, meaning if we have a conservative vector field, then this property is true right here. Where if we were to integrate our conservative vector field along some curve, then the value of that line integral is simply going to be the scalar function f evaluated at b minus f evaluated at a, where a and b are the endpoints of the curve. Okay. So let's first make sure that we're on the same page about what this means here in the first place, right? Maybe I'll just draw some curve like this with endpoints a and b. This. So what we're saying essentially is that conservative vector fields are the types of vector fields in which the only thing that matters when integrating a conservative vector field is the value at the various endpoints right here. In other words, this could be our curve right here, but we could also draw another curve that might look something like this. And as long as we're starting at A and we're going to B, the end result is going to be the same. So when we integrate conservative vector fields, that is the convenient case where the path in which we take does not matter. We're going to get the same result every time. Okay. Now, one more thing here too that I want to just make sure we're clear on is that the resulting value of the integral is the scalar function evaluated at b minus the scalar function evaluated at a. As we end up proving this, because we're going to prove this theorem here, we're not just going to state it, we're going to see why that's the case, but I just want to make sure that we're clear that this is the scalar function, not the vector function, or the vector field. And that's why in the previous whiteboard we said, okay, well, how do we go about computing this lowercase f quantity, right? Because if you're told that your vector field is conservative and you're able to find the value of this, or you're able to find what the scalar function is, then all you need to do if you want to integrate along a curve is you just say, all right, where do I start and where do I end? And then you just plug in f, your scalar function, evaluated at the endpoints. So that's the power of this. That's the convenience of doing this, okay? Now let's go through proving this. I'll say too that as I'm just starting to write this out here, that even though this is an applied math class, that doesn't mean that we're going to be completely devoid of proving things. In the end, it's still good to understand why this is the case rather than just stating it. So I'm going to start here with, let me even go back a little bit. Let's just define some stuff in the beginning. So if we have a line integral over some curve C, then let's say that, let's define a parameterization for that curve. We talked about a couple videos ago that that's kind of the first step in doing any of these things, right? So let's define a parameterization, and we'll just be general. We're going to call it R of U. And then specifically, we can say that let's define endpoints for this single input variable U, right? We know that the vector endpoints are A and B, but we can say, and we can define endpoints as follows. Endpoints. We can say that R evaluated at some starting value of U. Maybe the starting value is alpha. And when we have R of alpha, that gives us our starting vector A. And then maybe we have some other finishing constant, beta, or when R is evaluated at beta, that gives us the ending vector B, okay? So that's going to be kind of the machinery that or the syntax for the machinery that we're working with. And now, if we were to integrate this curve, or if we were to integrate this vector field, I should say, along a curve, that will be the same thing as, I'm going to try to go down a little bit, that'll be the same thing as if we integrate, rather than f, the vector field, I'm just going to rewrite it as the gradient of the scalar field. So that's going to be the gradient of f dot dr like this. And then using chain rule, we can re-express dr in terms of du, which is the variable used as a single input for the parameterization. So we can write this as integral over c, gradient of f, and a dot product. Rather than dr, we're going to write dr over du times du, like this. All right. And now it's at this point, because hopefully this makes sense, right? This is kind of all stuff we've done before. But it's at this point where we're going to kind of make a bit of a jump. And I think the best way to understand this is for me to just write out what the jump is, and then we're going to explain, all right, well, how do we go from here to that next line? Okay. So it turns out that with this line right here, you can rewrite it like this. You can rewrite it as the integral of your curve. And you can rewrite it as the u derivative of f of r, which is itself a function of u. So that, and then one more set of parentheses, du. Okay. So the jump that we made was rewriting the integrand from the gradient of f and a dot product with dr du, and re-expressing it as the u derivative of f of r, where r is itself a function of u. Okay. So let's understand, how do we go from here to here, right? I can tell you it's true, and you can take my word for it, but let's make sure we understand it. So, and maybe I'll do this off to the side over here. So what I'm quite literally doing is I'm taking the u derivative of this scalar function f. So I can write out, I guess, df du like this. Now, in the case where r is just a scalar quantity, so it's actually a vector quantity, but let's just suppose for now that it is a scalar quantity, then what we could do is we could re-express this derivative using chain rule, where we would say that we have df dr du like this, right? So that would be the case where r is a scalar. But of course, that's not the case that we have here, right? F is a function of r, where r is now a vector function. It's how we define parameterizations, right? So in the case where r is a vector function, we can't divide by a vector, right? So we need to have some sort of alternative way of computing df du. And the way that you do that is you just kind of use Einstein's summation notation and rewrite this expression with subscripts like this. So now what you're doing is you're taking, oh, excuse me, I should not write this as a full derivative. I should write this as a partial derivative, right? Because f depends on each component. F is a function of x, y, and z, whereas r of u right here is only a single variable function. So because f depends on x, y, and z, we would have a partial derivative right here. But because r only depends on u, that's why we have a total derivative right here, right? Anyways, this would be the expression in the case where r is a vector function. You simply take the partial derivative of f with respect to the ith component, and you multiply it by the u component, or I should say you should multiply it by the u derivative of the ith component. Now, so I guess hopefully this kind of makes sense. Like, that's how we would apply chain rule if we have a vector quantity. Now, again, just to make sure we're absolutely clear, I already mentioned that we're using Einstein's summation notation, and that is kind of a prereq for this video series. But in case we're unfamiliar with this, the fact that I have repeated indices over I implies that there is a summation over I in the first place. So this is really like partial f partial x dx du, plus partial f partial y dy du plus partial f partial z dz du. Okay? There's an inherent summation over I, and I indexes x, y, and z. Okay? So that's how we should read this expression right here. So if we understand that, all we have to do now is we can say, well, let's look at this quantity right here and see if it looks familiar with this, right? In other words, how can we re-express this integrand right here using suffix notation, Einstein's summation notation? Well, starting with the gradient of f, that is simply just taking the partial derivative of f with respect to the ith coordinate, right? That's how we'd express this in summation notation. And if it's in a dot product with this quantity, that means that we just need to write out this vector right here, and the index that we use for that vector is the same one that we use for this vector. That's how you incorporate dot products in suffix notation. So writing out this vector component-wise is simply just saying dri du like this. And we see that that's actually exactly what we have right here. So it turns out that this expression is in fact identical to this expression. Again, I realize that I'm going through it somewhat quickly because I'm assuming that we know Einstein's summation notation. This is something that you're really going to want to make sure that you understand, or else a lot of the proofs in this video series just might be a little bit confusing. Okay. So, point is that this is what we get right here for our overall line integral, and now it's just a matter of applying the fundamental theorem of calculus, right? And actually what I should do here is, now that I'm integrating over u, I don't need to use this notation of subscript c, but I can implement the endpoints, right? So this starts at alpha and ends at beta, this starts at alpha and ends at beta. And now we just ask ourselves, well, what is the value of a definite integral where we are integrating over u and the integrand differentiates with respect to u? Well, that's simply just the value of whatever is in parentheses right here, evaluated at the endpoints, and you take their difference, right? And this is why the resulting value of f dot dr is lowercase f evaluated at the endpoints, because we have lowercase f right here rather than uppercase f. So by just applying the fundamental theorem of calculus, this is going to give us f evaluated at r as a function of u is set to beta here, like this, minus f evaluated at r of alpha, like this. And then we've already specified that r of beta is just b and r of alpha is a. So we could just rewrite this line now as saying this is just f of b minus f of a. And that's what we were trying to get right here. Right? So hopefully that makes sense. For conservative vector fields, you can always do this. Now, one immediate follow-up result, which is also very nice with conservative vector fields, is to ask the question, well, what happens if the curve that we're working with is in fact a closed loop curve? And I think we were talking about that in the last video, right? A closed loop curve is just a curve that has the same starting point and ending point. And to illustrate this, what I'm going to do is I'll draw this over here. Is let's say that we have our endpoints A and B, like this. And maybe this is my curve going from A to B. So I'll draw an arrow indicating that we're starting at A, going to B. I'll call this curve C1. I could alternatively draw another curve like this. And maybe it's just starting at the opposite point. So maybe this one starts at B and then goes to A. And I can call this C2. Then the sum of these two curves together, C1 plus C2, you have C1, and then when you add C2, you get back to that starting point. So in this case, if we were to define C to be the sum of those two, then we would say that C is a closed loop integral. Okay. So now what I want to do here is, let me actually write this over here. We're going to say that C is the sum of the two curves, C1 plus C2. So what I want to do next is I want to say, well, let's integrate over this closed loop curve C. So let's perform the closed loop integral over C of a conservative vector field F dot dr. Okay. Now, if we were to do this, we immediately know the value of what this is. That's just given by this theorem, right? It's just f of b minus f of a. Or let me at least first, or it's f of the starting point minus f of the ending point. To make this clear, what I'm going to do is I'm going to say that this closed loop integral is in fact the sum of the line integral over C1 f dot dr plus the integral over C2 f dot dr, like this. Okay. And I realize I'm running out of room. I'm going to try to write it in this final line, and I hope that we can see this down here. But let's ask ourselves, what is the integral over C1 of f dot dr? Well, that's just if f is conservative, which we're saying it is, then that's just lowercase f evaluated at the endpoints, the ending point minus the starting point. So let's ask, what is the ending point and starting point for C1? Well, C1 ends at B and starts at A. So this integral is f of B minus f of A, like this. But now we need to add on our second contribution. And I'm just going to erase this just so I don't run out of room. Now we do the same thing here. What's the line integral of f dot dr over C2? Well, same thing. It's just the value of f at the endpoint minus the starting point. But in this case, C2 starts at B and ends at A. So now I'm adding the ending point of C2, which is A. So now I'm adding f of A, and I'm subtracting its starting point f of B, like this. And then you just look at this and everything cancels, right? Minus f of A plus f of A, and then f of B minus f of B is 0. So this is another really convenient property of conservative vector fields. If you were to integrate a conservative vector field along a closed loop C, then you're guaranteed to get 0 as the output. And hopefully that kind of makes sense, right? That if you're integrating along C1, you're going to get some value, but as long as you know the starting and ending point, you're going to get the same value no matter what. So if you go in the negative direction, you're bound to just get the negative of that same value. So you get something minus itself, and it's always going to give you 0. Okay. So hopefully that makes sense. A lot of nice properties that are very convenient to work with in conservative vector fields. And some of these properties are why people love these things in physics. Okay. Now, the next question that we can ask, which is probably the natural one, is, well, how do we determine if a vector field is conservative, right? We talked about how we could find this lowercase function f, assuming that the vector field is conservative. But as you could probably imagine, what actually ends up happening in a lot of problems is you're given some vector field f, and you want to know if it's conservative. Because if it is, then you can utilize some of the nice properties. First one being this right here. I know there's a lot on the board, but the first one being this, and the second one being this right here, right? So you want to be able to utilize those, but you got to figure out that if f is conservative or not. So that's what we're going to do next. We're going to go through some kind of a criteria that is easy to perform that determines whether or not a vector field is conservative. All right, so this claim here, this is kind of the criteria that gets used to determine if a vector field is conservative. So let's go through it together. It says here that a vector field is conservative if this criteria is upheld, where we have partial fi, partial xj is equal to partial fj, partial xi. All right. Now, first thing that I want to make clear before we go about proving this is that we use Einstein's summation notation throughout the video series, and we're using it here in the sense, or I guess we're using suffix notation in this equation right here, but we are not summing over any quantity. Notice that on the left-hand side, we have one factor of I and one factor of j, and so we should have the same thing on the right-hand side, which we do, right? We have one factor of I and one factor of j. You only have a summation over some quantity if a given term has two factors of that associated variable. So if you had two i's or two j's for just this term, then there would be a sum. But because there's only one of each for this specific term, no summation is applied here or here. Okay. So I just want to make sure that's clear. There's no inherent sum over this. This is quite literally this term equals this term. Now, how do we go about proving this, right? And to prove this, it's actually relatively short. What you would do is you would just start with the definition of a conservative vector field, like this, and then you would rewrite each component in suffix notation. So this is a vector quantity, so it can be denoted with a single index, and maybe let's just call it I. So the ith component of this vector f is f sub I, or uppercase f sub I, like this. And this is a vector, so this is also a vector quantity right here. And this gets expressed as partial f over partial xi, right? That's how you would write out the ith component of the gradient of lowercase f. And this, we've gone through this before, I think, right? So this is the equation that you have. And now all we have to do is we have to substitute that into here. And maybe just to make this absolutely clear, this is what the relation looks like if your index is I. If your index is j, it's the same thing. It doesn't matter what you call the index. It's that, in this case, the jth component of f is equal to partial f partial xj. Right? So now let's just take these two expressions and plug them into this equation. So on the left, we have the derivative with respect to xj. So we have partial xj. And then we have the derivative of what? Well, it's the derivative of fi, and we said that fi is this quantity right here. So it's the derivative of partial f, partial xi. Now we have an equal sign, and now we're taking the derivative with respect to xi, so we have partial over partial xi, and we're differentiating fj, where we said that fj is just this quantity right here. So we have partial lowercase f, partial x, j, like this. And now we can just apply the derivatives on both sides of the equation. So this left-hand side would be partial squared f, partial xj, partial xi, and that would need to equal partial squared f, partial xi, partial xj. And these are known as mixed partial derivatives, where you first take derivative with respect to I, then j, and then vice versa right here, and it's just a known property that mixed derivatives are equal to each other. In other words, if you differentiate with respect to I, the ith variable first, and then j, that gives you the same result as if you differentiated with respect to xj and then xi. So because mixed partial derivatives are equal to each other, then therefore this original identity is valid. Okay. So hopefully that makes sense. Now we might be saying, okay, I can see how you go from here down to here and how you show that those are equal to each other, but how do you actually go about applying that, right? Because it might be a little more confusing to apply it. So let me just get rid of the i's and j's, and then we'll just work in standard three-dimensional Cartesian coordinates. And what we could do here is, I think what I want to do, I want to erase this right here, because that was just the proof in itself. And I want to show how you would actually go about applying this in Cartesian coordinates. So whether the three-dimensional Cartesian coordinates. So if you're working in 3D Cartesian coordinates, your three different variables that I and j can index from are x, y, and z. So for example, if I is equal to 1, or maybe like your x coordinate, and j is your second or your y coordinate, then this is what this relation would result in. you would have partial f, and then instead of I, we're going to write x. So partial the derivative of your first component with respect to xj, and if j is your second coordinate, the second coordinate is y, right? So you'd have partial fx partial y equals, now here we have partial f, and instead of j, we're going to write y. So now we have partial fy, the second component of f, with respect to the first coordinate, which is just x. Okay, so hopefully do we see how that works? You could take your vector field, which is going to have an I hat, j hat, k hat component, and if you could say that the x component, differentiate that with respect to y, if that's the same as the y component differentiated with respect to x, then this identity would be valid. Now, we're trying to make a point here. We might be saying, well, why write these i's and j's rather than be a little bit more specific, right? And the reason is because this identity is going to hold true in any number of dimensions, not just 3 dimensions, and with any pair of coordinates. So in this example that we had right here, we set I to be the x or the first component, or the x coordinate or first component, and j we set to be the second component, or the y coordinate, right? But this would work with any 2 coordinates that we pick, right? We could now set maybe, we could set I to be z if we want, right? So then we would have partial f z, and then with respect to partial, now maybe j is no longer corresponds to y, but it corresponds to x. So now maybe we have partial fz partial x equals partial f x partial z, right? And then I think just to complete it, let's see, then we have x and y right here, we have x and z, so now we need y and z, right? So then this would also be valid. We'd have partial fy partial z equals partial f z partial y, like this. So this general expression is just a compact way of writing each of these 3 equations right here. And it's saying that no matter which of those equations you look at, they're all going to be true. Now, to make sure that we're clear about this, because this is the criteria that we would use to actually test if a vector field f is conservative. This identity needs to be true for any 2 coordinates that you pick. In other words, if you pick this one, it needs to be true. If you pick this one, it needs to be true. If you pick this one, it needs to be true. Another way of saying that is that it needs to be true for all of them. So when you're trying to determine if a vector field f is conservative, you would need to go through each of the different possibilities and determine if all of these equations match up. If even one of them doesn't match up, then your vector field is not conservative. Okay. So it can be, you can imagine that as you get to higher and higher dimensions, this test can quickly become kind of tedious. But in 3 dimensions, you have 3 equations. In 2 dimensions, x and y, this is the only equation that you have. It's not so bad in those cases. But that's what you're going to have to do if you want to show that a vector field f is conservative. Right. So hopefully that makes sense. Now, next thing that we're going to do, and this is going to be the last thing that we do to finish out the video, is when talking about a conservative vector field f, there are some other quantities that arise from that. And we're going to show that first what those quantities are, and second how they can be useful for solving different types of problems. All right, so now we have this thing here called an exact differential. So let's unpack that together. It says here that a differential f dot dr is considered exact if there's a scalar function f such that the vector field uppercase F is the gradient of that scalar function f. Okay. And really, this is just a long-winded way of saying if your vector field uppercase F is conservative, then if you take a dot product f with a differential dr, the overall product, the dot product, is a corresponding differential, right? It would be f of x dx plus f of y dy plus f of z dz. Each of those are differentials. And it's essentially saying if this is conservative, then this dot product here is, or yeah, it's considered exact. It's called an exact differential. Okay. Now, we can be like, okay, cool, that's a term, right? But let's see why this can be useful, first of all. And I think the main idea here is just to introduce the terminology, because you're going to see the term exact differential show up throughout the video series and I believe the problem sets. But let's just show what we're able to do with kind of what we know so far about conservative vector fields. So I'm going to start by just integrating. Let's try to make it look a little, all right. We're integrating over some curve C, and we're performing a line integral of f dot dr, and f is a conservative vector field. Then what we know is that we can re-express this line integral as the gradient of a scalar function f. Same idea in a dot product with dr, like this. And then what we can do is we can say, well, let's now re-express this differential in this, which is an exact differential, in using Einstein's summation notation. So we can rewrite this as an integral over a curve. This expression right here, this could be rewritten as partial f partial xi. By the way, too, I'm not doing it in this video because I'm not trying to make it too confusing, but I do want to use this notation when I can, and throughout as we get later on in the video series, I'm going to use this notation. Another way of writing this quantity right here, maybe I'll just write it up here. Another way of writing partial f partial xi is simply to write partial I of f. This is saying we're going to take the derivative of f with respect to xi. So that's a common notation. To avoid the potential confusion, I'm not going to do it now, but I want to make it clear because I will be using that later. Anyways, this is how we can write the gradient of f using suffix notation. If it's in a dot product with dr, that means that we need to write dr or we need to write the vector component is dr as dr sub I. So they have the same components like this, so we know that there's an implied summation, which is the equivalent of taking the dot product between these two quantities right here. So, or let me actually just rewrite dr as dxi. I'm kind of using them interchangeably, but that's what we have right here, right? So now, what I'm going to do is I'm just going to more or less rewrite where this partial xi is in the integrand. Right now it's in the denominator of this fraction, but I'm just going to move it so that it's under this dxi over here. So we could rewrite this as, now I guess df, and then we just have, I guess, dxi like this. And of course, this is just something divided by itself, so it cancels. So another way of writing this line integral here is just the integral of df, like this. And that kind of makes sense, right? That like, if you're just integrating a quantity df, then the ultimate value is just going to be f at the endpoint minus f at the starting point, which is what you get if you perform this line integral, right? Now, you might be saying, okay, sure, we're doing these manipulations, but why do I care, right? Why is this convenient? Why is this useful to me? And it's a good question. And the answer to that is because in some problems, you're going to be given an expression that may not look like you're working with a conservative vector field. It would be the case that you are working with a conservative vector field, but it might be written in a way to try to prevent you from immediately seeing that. And the idea is that we're just saying that this is an alternative way we're trying to say if you can express your line integral like this right here, that is another method that you can use to recognize that you're integrating along a conservative vector field. Even if you're not just explicitly provided, the vector field is this, and you're integrating along this path specifically. Okay. Now, I think this is the most clearly seen if we see a specific example. And so that's what I'm going to do. I'm going to write out an example, and we're going to see that just looking at it, it doesn't immediately pop out that we're we're integrating along some conservative vector field, and how we can use this notation right here to help us find the value of that integral before we go into doing too much work that's not necessary. Okay, so we have an example integral right here where it's not going to read it. I mean, we can see it itself, right? It's this long integral over some curve C, and if you were to break it into components, you'd be integrating with respect to dx and then dy and then dz. And let's say that we're given some starting point vector A and some ending point vector B, right? Now, if we just look at this integral, we might initially say, well, first, that's a long integral, right? And then we say, okay, well, how do I perform line integrals? And then we're going through our notes, trying to remember what do we do to perform line integrals. And we see, okay, well, I got to first figure out what my curve C is right here. I got to perform some sort of a parameterization so I can rewrite X, Y, and Z in terms of some single variable U. And then you got to go through each of these components, and there's a lot of work in doing that, right? What you could do is you could just say, well, let me hold on a second, and let's just see if this quantity right here comes from a conservative vector field. Now, if it does, then this component right here should be the derivative of a scalar field with respect to x. This quantity should be a derivative of a scalar field with respect to y, and this quantity should be the derivative of a scalar field with respect to z. All partial derivatives, of course. So we can say, all right, well, if this should be partial f, partial x, let's just see what happens if I were to take the antiderivative of this with respect to x. We look at it and we say, okay, well, x only shows up one time, and it's right here. And taking the antiderivative just results in, that's just power rule, right? So this becomes x cubed over 3. The 3's cancel out, and what we would be left with is x cubed y sine of z. Say, okay, sure. Then we go into this quantity, and we say, if this was equal to the partial derivative of f with respect to y, what would happen if we take the antiderivative with respect to y, right? And this is, y doesn't show up here at all, so this is just like a constant. So taking the antiderivative just means this quantity times y, which is x cubed y sine z, which is what you get right here. And then the wheels start turning in your head. And you say, okay, well, let's check this one, right? If this is partial f partial z, let's take the antiderivative of this quantity with respect to z. And then when we look at it, we say that, okay, that would be x cubed y sine of z. And it's the exact same thing in each of these cases. So what we realize is that without doing any other work, this integral can simply be written as the integral over some curve C, and it is d of f, where f is my scalar function. And we ask, what is the scalar function? Well, it's whatever that same quantity was that we found in each of those exact differentials, right? So it's going to be d of x cubed y sine z, like this. And now if you're just taking the differential of this quantity over some path, then you immediately know, without having to do any work, without having to find a curve, find a parameterization, and all of that, you immediately know that the value of this is simply going to be x cubed y sine of z, evaluated at whatever your starting vector is, a, and whatever your ending vector is, b. So you would just, so I guess that this had components ax, ay, az, this had components bx, by, bz. This would equate to x, or excuse me, this would equate to bx cubed by sine of bz, like this, minus ax cubed ay sine of, get out of the way, az, like this. And now you've immediately found your line integral without having to go through all of the standard procedures for performing a line integral that we've seen in the previous video. So this is a nice little trick. And again, just looking at this, it's not immediately clear that we're working with a line integral over a conservative vector field. So it can be very easy to fall into the trap of just, you see a problem and then you just start doing calculations, because that's kind of what our brain gets wired to do when you do enough of these problems. And this is just a little check. You can always do this. You can always perform the check. And if the check doesn't work out, right, like if you don't get the same quantity here, here, and here, well then yeah, then you do need to find a parameterization for your curve, and you do need to rewrite everything in terms of some single parameterization variable, whether it's u, theta, t, whatever. You'd still have to go through all that, but this could potentially save you a lot of time if it does in fact work out. Okay. So that's why this stuff gets introduced. Now, I think this is a good time to stop, and we'll call it here. The next video is going to be the start of a new section where we start to look at these quantities called surface integrals. It turns out that integrating along just an arbitrary curve is not the only way which we can generalize the integral from single variable calculus. So that's what we'll be covering in the next video. So yeah, thanks so much for watching, and I hope to see you then.